my where filter says where author equals whatever. And the other common query is where author equals whatever and title equals whatever. Okay, so take a minute with the person next to you, give me a secondary index that will help those two queries. Author and title, all in one. Okay, so yeah, I kind of intentionally wrote this in a way that might trip you up. But so notice the second query here is searching by title and author, but and doesn't care the order of the arguments. But since we want to support both of these queries, putting author then title supports searching just by author. And then it also supports searching by and for both of them. Okay. This would not work. Title, comma, author. It would help the second query, but it would not help the first query. So whenever I give an exercise like this or a problem like this, I want the minimal set of indexes that will support those queries. So you could do this. You could make like title and author. That would help the second query. But then you'd need another index on just author. Or you could just do this one index and get it kind of two birds for one stone. So the reason for this is, and here's a different table going back to like LMS classes. So if I have an index on department comma num, basically all that does is put the two keys together, and that becomes the new key for the index. So this obviously helps if I'm searching with and for both keys. But it also helps if I'm just searching for whatever the first one is, department, because I can just look at the first few letters, and those keys are going to be sorted by department. It does not help with searching by num because these compound keys are not sorted by num. They're sort of sorted by num, but only within clusters. So all of the CS nums are sorted relative to other CS nums, but are not sorted relative to every other number. Okay, so a multi-column index it's basically sorting with a tiebreaker. So you have the primary, comparator, which would be like A, and then anytime there's a tie, you use the secondary comparator, and you get these clusters of sorted primarily by A, and then each cluster is sorted by B. Okay, what about this? If we want to search using or instead of and. So, it could be title or author or title. Again, it doesn't matter which one I put on the left or right. What's an index that would help with this? Or is there one index that can do this? Yep. Yeah, we need two. We need one for title, one for author. If you combine them together, it would kind of help. So if you had a combined index and you were searching for title or author, and let's say the combined index was title then author, you could go and search for the title part, and if you get lucky and find one, then you can short circuit and return true. But if you don't, then you have no good way of searching by author. So to truly support this query, you have to have both of these indexes. Yep.
So what would be the complexity of searching by author and title?
So what's the complexity if you had the index author, comma, title? In the average case, it's linear. Well, assuming that average means you have to search both keys. In the good case, where you find the author, then it's based on whatever kind of data structure you use. We'll say it's a tree, then it's going to be logarithmic. So if you get lucky, and so you're searching for, like, say Herbert is the author, Dune is the title. You might have other Dune titles in there, but not by Herbert. So if you search by Herbert first and don't find anything, then you have to go do a linear search for the book Dune, since you don't. On an and? On an and, it's just logarithmic. Yep. But in the or case, if you have a book by author, by Herbert, then and say you start your search there, then it's logarithmic if you find that author. Okay, any other questions on it? It gets kind of subtle, the difference between and or and how they relate to indexes.
So, how much overhead is there for like a single index on the table?
How much overhead is there for a single index? The index takes up space. Turns out not as much as a whole table containing records, but it does take up some space. And then it also, every time you change the table, you have to update the index. So depending on what data structure the index uses, that basically determines the overhead. We'll be pretty much using trees, so you get logarithmic performance. Any update is going to be logarithmic. Yeah, so there is overhead. It's not free. But logarithmic in terms of performance, but what's more important is what is the behavior in terms of number of disk pages accessed. That's what's going to dominate the time in doing any kind of database operation. And we will get into that today. That's basically what today is about, is how do these indexes work. Okay, so kind of just to summarize, an index on AV is not the same as an index on VA. They support different kinds of queries. And an index on AV is not the same as an index on A plus an index on B. So a multi-column index on A and A comma B is good for searching by both of those with and. It's good for searching by just A. It's bad for searching by B. Two single column indexes is the best option you have if you're searching by or. It's bad for searching by and, it's good for searching by A alone, and it's good for searching by B alone. So I put kind of best option in yellow here. It's not like this is going to support it extremely well. You don't want to have two indexes, and in the average case, you're going to have to search both of these indexes. So it's yellow because it's the best we can do, but it's not as good as like having a two birds with one stone sort of index. Okay, so modifying, dealing with indexes, there's the create statement we've already seen. You can also remove an index if you decide you don't need it. That will save space. That will make all queries that modify the original table faster. And you can just examine them by using show index. Okay, so pretty straightforward. Now, back to this question of why do these indexes exist? Obviously, they make performance faster. But what are the special issues we need to deal with because this is a DBMS and not just any old program? So remember, a database, it has no choice but to store its data on disk. And this even includes like during runtime. So it's not like you load some file from disk and then the whole thing exists in memory while the program is running. It's like while your program is running, you're constantly going to disk just because the space of the data is so huge. So now you kind of use RAM like a cache and try to keep as much in RAM as possible and avoid going to disk. So we have to go to disk. So how can we avoid doing it? Well, first of all, the problem is huge. Like, it's going from cache to RAM is really bad. Going from RAM to disk is really, really bad because of the mechanical nature of the disk. It just necessarily takes a long time to move things, moving physical things. So what we can do, and what the OS does, and the database management system can even bypass the OS and do its own smart things with the disk if it wants. But we'll look at just what the OS does, is it's going to read a lot of information anytime you request data from the disk. It'll read like 8 sectors, which makes up one 4K page. So if you can organize your program in such a way that if you have to load a page, try to reuse as much within that page as possible, then you can avoid going to disk. But if you're just totally randomly jumping all over the disk, then every access is going to be super slow. So kind of to summarize, going to disk is bad. Databases are huge, so we have to go to disk. How can we make our DBMS aware of this and mitigate the problem? So we don't want to have to just obviously search through an entire table every time we do something. So we have indexes. But the index itself can be very big and has to live on disk somewhere. So let's look at the basic goals of an index from a performance standpoint. All I've shown so far is that there's some structure that is like meta information that organizes pointers to the real data, and it organizes those pointers in different ways. So what is the actual data structure that implements the index? We want fast insertion, fast deletion, and fast search. Specifically 2 kinds of search. So we do a lot of range queries in databases, like greater than some date or in between 2 dates. And we often do a lot of just exact match queries. So think back to your algorithms and data structures class. What is a data structure that supports this? BST. So we have fast insertion and fast deletion with a BST or a hash table. Hash table is a little faster. BSTs support range queries. Hash tables do not. So overall, like kind of best option is going to be a BST. And then there is a 4th criteria here, though. We also need for all of that stuff to happen and touch as few pages as possible while doing these operations. So insert, delete, and search. Whatever data structure we use, we want it to be fast in terms of like asymptotic behavior. We also want it to touch as few pages as possible. So we'll start with a BST. That is a good starting point. It handles the like kind of algorithmic parts very well. And then we'll look at how does a BST perform when you're dealing with a giant tree that's spread across many pages, and how can we avoid touching many pages? Question back there? Binary search tree, yeah, BST, it's binary search tree. And this is just because I'm starting here because I know you're all familiar with the BST. Turns out we won't end on a BST. So, okay, let's say that we use a BST to make the index. Then essentially what that means is I have the table itself, plus I have this other data, which is the tree. And all the tree holds is keys plus like pointers into the actual data. So the tree, the data itself is not held in the nodes of this tree. The tree is just, whatever, let's say I built this index on class num. So the tree just holds those keys, and then each node could have a pointer to somewhere on the disk, like a sector and a location within that sector to get to the row. Okay. Then I can build another index on name, for example. It's a different BST, so it holds different keys and it's structured differently, but it has pointers into the same table. So you can have this big mess of pointers coming into the table from all different kinds of indexes. And any given row in the actual table might have pointers coming into it from various indexes. Okay? So the tree itself has to reside on disk somewhere. Remember, we're dealing with massive data, so the tree might even be massive, even though all it holds is indexes and pointers. But there are lots of indexes, or keys, sorry. It holds keys and pointers. So the tree might occupy many disk pages. So let's look at how do we actually build this BST. Every time we insert a node into the tree, we need to essentially allocate a new node. In Java or whatever, when you're building your BST, when you need a new node, you just say new node. And that just gives you a node somewhere in memory. But we have to think about where we're putting this stuff on the disk. So our allocation strategy, a very simple thing to try, is just keep track of whatever the current page is that you're filling up, and just put the new node at the end of the page until that page is full, then get a new one. Start putting nodes in there. And then all you need to do is make sure that the pointers all go to the right places. So they might be jumping all over pages. But let's try this and see what we end up with. So I'm going to insert a bunch of nodes into an empty tree. So I'll insert I. I is the key. So I make a brand new root node with I. And we're going to look at this in the context of pages. So I'll start with this kind of like light blue page. And in our example, we will say that a page can hold 3 nodes. So I get a new page, I put I into it, this is the current state. Now I'm going to insert J. I still have room in the light blue page, so I put it in there and I update pointers so that my tree structure looks like this. Because J is greater than I, so it goes to the right. Insert D, tree looks like this. I've now filled up the light blue page. It can only hold 3 nodes. Okay. Insert B. That's where it has to go in the tree, but I have to get a new page for it. So I allocate the red page, or just find the red new page available on the disk. Add F goes in the red page. Add A goes in the red page. So there are kind of 2 constraints here. The tree has to have the BST structure, and I'm just putting these, just filling up pages as I go along. Add H, we need a new page. Add E, add C, add G, and that's all we're going to add. So I've added I, J, D, B, F, I forget the order, but basically like A through G, H, I, J. A through J. And this is just what we ended up with if I can fit 3 nodes per page. So where we put them in terms of pages was purely based on the order that they were added to the tree. But the structure of the tree is just BST structure. Everything to the left is less than, everything to the right is greater than for any given node. Okay. Now let's look at using this tree to find something. So we're going to search for G. And we're going to look at it in terms of what pages do we have to touch to get there. So we start at the root, obviously. So we've loaded the blue page. We get all of this stuff in the blue page. So we have D and J in memory now. I can go to the left without visiting a new page. I go to the right, and that means I have to load the page containing F. Okay, look what's going to happen now. I've loaded the entire red page, and now I'm going to just skip down to H. So I basically just very quickly skipped across the red page. I touched it once and then moved on. Loaded B and A from disk into memory, and then just didn't use them. Now I go down to H, I load the whole green page. Go down to G, I load the whole yellow page. So essentially I loaded every single page to get to this leaf node. How many nodes did I actually visit during traversal? 5. So I could do, in the best case, I could do that in 2 pages, if these pages were kind of organized differently. What I would want basically is like somehow to end up with that being 1 page and that being 1 page. Okay. So 2 problems here. One is the tree is not balanced, so it's a little deeper than it needs to be. And the bigger problem is that the tree is not organized with page reuse in mind. So we look at these 2 pages here. We loaded a full page to touch 1 node. And that's because these pages are they're horizontally organized instead of some other better organization. So we jump to some level in the tree, load a full page to do it, and then jump out of that page immediately down on the next level. So let's fix the balance problem. Maybe we use an AVL tree, a self-balancing BST. I use the same insertion order there, but if you use an AVL tree, you end up with this. The balance is better. So the height is lower, but the same nodes are in the same pages, just because that's how we did it, and it's like just as bad in terms of getting reuse out of pages. To get to G, I would still have to load every page, light blue, green, red, and yellow. So what we need to do is use, if we're thinking of trees, we need to somehow reorder the tree so that during traversal we can get reuse out of a page. And so let me go back and kind of draw on one of these diagrams. So what I did was I said, well, we wanted the pages to be ordered something like this. That would be better. So these are like taller pages rather than wider pages. And that helps for this particular path. But what if I was searching for J and I had to come down here? Then this page organization doesn't help. What if I was searching for, I don't know, C? Then this page organization helps a little better, but basically you cannot predict whether you're going to go left or right, so you cannot make a page that follows the path that you need. So here's the more general problem, is if we're using a tree, then we can't really predict the insertion order, and thus we can't really predict which page a node will go into. And as this tree gets very, very large, the number of pages accessed to get to a leaf node becomes proportional to the height of the tree. So this is a very tiny tree. In a database, this tree would be extremely deep, and there would be like millions of nodes at the bottom level. And on average, you're going to have to go down to the bottom level to find what you're looking for. So we need to reduce the height, basically. If height is the problem, height is proportional to number of pages accessed during traversal, we need to reduce the height of the tree. So what's a super easy way to reduce the height of a binary tree? Partition it into 2 trees. Okay, that's along the right lines, yes. That would split it into 2 trees, would reduce the height of each of those trees. We want to keep it into like 1 data structure. Balance them, assuming if it's already balanced. How can we reduce? Let me rephrase the question. I said, how can we reduce the height of a binary tree? How can we reduce the height of a tree?
Just put put more nodes per node.
Increase the branching factor. Instead of a binary tree, let's look at a quad tree. So this is a quad search tree instead of a binary search tree. We have 4 children per node. So the branching factor is 4. This greatly is going to reduce the height of the tree. The way this works now is each internal node is going to have 3 keys in it. So if you look at a binary tree, you have 1 key and then basically a pointer on either side of it, to the left of and to the right of. If you want a quad tree, you put keys basically in between all of the pointers. So you have one to the left and right of every key. And basically the way this works is these internal nodes here have to be ordered so that you can look through them until you get to the one where you're in between, say, like F and I. Then you follow that branch if that's what you're looking for. Okay? So this is like the same tree, same keys, but built into a quad search tree instead of a binary search tree. We still have 3 keys per page, but now look at the page organization. And one node fills up exactly 1 page. So we don't have any kind of weird like page arrangement to worry about. We have, like, if you load a node, that's equivalent to loading a page. So each traversal step now requires more computation. Instead of doing 1 comparison to figure out if I go left or right, I have to do a bunch of comparisons to figure out if I go down branch 0, 1, 2, or 3 at each node. So there is more computation per step, but there will be fewer steps because the tree is shallower. But if you're worried about this computation per step, that's just computation. The higher cost of loading the page has already been paid. All of this computation is within RAM now instead of within disk. Okay? And so what we've done is drastically reduce the height of the tree, and now we can find any key we're looking for in exactly 2 page accesses. No matter what, we can get there in 2 page accesses.
So what would be the time complexity of like quad search? Is there like some sort of ratio for
Time complexity turns out to actually be still logarithmic, like same as a binary search tree. You have fewer steps, but more work per step. And within reason, like ternary and quad trees, the big O time complexity turns out to be the same.
maybe you can get into this, but what's the cost of balancing?
Okay, what's the cost of balancing? So there's one more thing I haven't really talked about here, is that this tree is perfectly balanced. And the way that we do that is we don't use well, it's obviously not a binary search tree. It's a more general form of a search tree that is always perfectly balanced. So we don't need to do like tree rotations, AVL stuff like that. We end up kind of building the tree in a different way such that it is always balanced. Every leaf node will always be at exactly the same depth. So this is actually called a B tree. It's a generalization of a balanced search tree. So the B stands for balanced, not binary. And in fact, the branching factor is usually quite wide in a B tree. So it could be like 10, could be like 100, like super wide trees. And they're constructed in a very different way. You don't do these like red, black, or AVL tree rotations. You kind of build them from the bottom up rather than from the top down. And we'll see how that results in an always balanced tree. So we're actually going to be looking at a B+ tree, which is a B tree with a slight tweak. There's minor differences between a B tree and a B+ tree, which I'll get to in just a second. But not terribly important. The basic idea is it's a generalization of a balanced search tree. Okay, so the internal nodes, so every node itself is an array now instead of just one thing. And depending on the branching factor, that determines the size of the array. And then the way that these branches work is to the left of a key means everything following that link is less than the value of the key. To the right of a key is greater than or equal to the key, so that or equal to part is important, and less than whatever the next key is. So this one, like let's look at in between E and K. That means anything following that branch is greater than or equal to E and less than K. And then the one on the far right is just greater than or equal to R. Okay. So something to notice here is the keys are every key in an internal node is going to be duplicated somewhere down below. This is basically the difference between a B+ tree and a B tree. So there you go, that's the difference, essentially. The reason for this is the internal nodes have a different structure than leaf nodes. So internal nodes only hold keys and pointers. And then the leaf nodes hold all of the information. So whatever key, whatever information that key is referring to has to be somewhere in the tree. So you actually need to repeat the key in the leaf node because the internal node doesn't have the rest of the data. So like I have the R here, that's just the key R to tell me how to get to something with key of R. And then once I find it, there's more stuff down in that bucket in the leaf node. So this would be like multiple columns in a table. You have the primary key plus whatever columns are associated with that row. Okay, so the internal nodes are not going to hold the actual data. The leaf nodes hold the actual data, and the internal nodes are just the structure for getting there based on a key.
When you say actual data, are you saying that all of the data associated with the table at R is going to be stored?
So right, all of the data from the row with key R is going to be down in a leaf node somewhere. Yes?
Within the leaf node, does order matter?
In the leaf node, does order matter? Excellent observation. So the way I've shown this diagram, the internal node is sorted, the leaf nodes are not. And so this is actually an implementation detail. You could make it so that leaf nodes are sorted, but turns out we won't sort them because that'll be a higher cost than leaving them unsorted. The internal nodes do need to be sorted so that you can then actually find the right branch to follow quickly. The main reason for sorting internal nodes and not leaf nodes is that the leaf nodes are going to change much more frequently than internal nodes will. So you don't want to have to resort every time you add or delete something. Internal nodes are not going to change very frequently due to additions and deletions.
What happens when leaf nodes become internal nodes? Like when we branch?
So what happens when leaf nodes become internal nodes? We'll get to like how to build this tree soon.
How does it work if you needed to look between a range of dates without having to check every single date between your range and figuring out how to go down this tree?
So how does it look? How does it work if you're looking for a range? Once you get down to the leaf node, you basically look at the whole leaf node. So it is more expensive to look through a leaf node algorithmically, but we've already paid the bigger cost of loading that leaf node from disk. So it's like, it's a trade-off where like it's okay to have to kind of search through the leaf node in an inefficient way as long as we reduce the number of page accesses. So in a B tree, every leaf has the same depth, and that is the definition of perfect balance. So we are never going to have a suboptimal height for any B tree, which is going to guarantee a minimal number of pages accessed to find anything we're looking for. And then finally, so this kind of goes along with the question of like, how do you do range queries? What if the range query would span multiple leaf nodes? Basically what you do is the leaf nodes have a pointer to the next leaf node. And that way these nodes at the bottom form kind of a linked list, but it's a semi-ordered linked list where the items within a page are not necessarily ordered, but everything in the left page is less than everything in the right page. Okay. So let's take our short break now, and then we'll see how to actually build one of these. I'm going to do an example where 2 keys will fit per node, just to keep things simple. So it's not like this where we have 3 keys per node. We have 2 keys per node. That makes it a trinary tree. And so I'm going to start from scratch, and I'm going to add I, then J, then D, then B. That's the same first 4 nodes from the binary tree example that we did. So we start out, we have to make a new node. And it's both the root and a leaf node, because it's the only node. And each one of these can hold 2 things. So the first thing we do is we put I in one of those spots. Okay. Now we are adding J. We have room in the sole leaf node, so we just put it there. Okay. Tree is balanced. Easy. Now, so the next one, so we've added I and J. Now we're going to add D. We don't have room for it in our existing node, so we need to make a new one. So this is where it starts to look different from constructing a BST. Instead of making a new child, I'm going to make a new sibling so that we're guaranteed they're going to be at the same depth. Then I will eventually add a parent that links these 2 together. So now what we do is, so remember, I'll go back a little bit. So remember, we have to end up with this semi-ordered linked list for the leaf nodes, which means that I, J, and D have to go into these 2 nodes in such a way that the left one, everything in the left one is less than everything in the right one. So I need to now redistribute my existing node. I have I and J in there. I need to end up with I and D in there, and J moves over to the new node. Okay? And notice I did not sort I and D. In a real implementation, you might actually sort them during this redistribution process. Now, this is not a tree. This is just 2 buckets. So what we do is, as I said, we're kind of building from the bottom up rather than from the top down. So we create a new parent for them. And we have to have some way of getting to the children given this node. What we do is we pull in the smallest value from the right node as the key. And then, so internal nodes are different. Internal nodes have little pointers here. So now this pointer goes to here, and this pointer goes to there. Okay? I have a perfectly balanced tree, and I didn't have to do any tree rotations or anything. Let's see. Next is adding B. So I can't put it here. We have space there, but I can't put it there because B is less than J. And it's not because of this J. It's because of this J. So when finding, where do I want to put a new node, we basically traverse down the tree. So I would say, all right, looking for a spot to put B, so I start traversing downward. So I look at the J, like, okay, B is less than J, so I would want to try to put the B into that node. That node is full, so I have to split it and redistribute. So I make a new node, redistribute so that everything in the left is less than, which means we end up with B and D. So the D moves over. Okay, and then we have to promote something to be a new key in the parent in order to find how to get here. So I take the smallest thing in the right node, which is I, and I needs to become a new key in the parent. But if I put it there, now I have an unordered internal node, and I've violated the properties here. These pointers are not going to the right place. You need everything to the left of a pointer to be less than it, everything to the right of a pointer to be greater than or equal to it. So this is where I have to resort the internal node. So I kind of erase some existing pointers here. I put I and J. To the left of I is that node. To the right of I is that node. And to the right of J is that node. There's lots of like fixing up pointers, propagating keys up into parents. But notice I only had to actually do a sort operation on the internal node. I'm free to leave leaf nodes unordered. They happen to be ordered as is right now, but that's not a requirement. Okay. I can add a few more things to this, and depending on their values, I may or may not have to create a new page to do it. If I do have to create another leaf node, then what I would do is end up with another internal node and a new root node if I had to do that, because my existing root node is full. So basically, anytime you need to add something, if the page is full, you split and redistribute and create a new parent, or a new key in the existing parent, if there's room for a new key. Okay? Any questions? Yes?
So if you were to insert something like C next, which is less than I and less than D,
Yep.
is that going to make it so I and J becomes an internal node, or is it going to have
Yep.
to create something?
So if I were to insert C next, I would have to make a new internal node that is above, that is at the same level as this internal node. So it would go, either here or here, depending on how the redistribution happens. Yep. And so this looks like we're making new internal nodes all the time and everything, but that's because we're dealing with tiny, tiny pages. In reality, a page is 4096. Once you get a page, you can put a lot of stuff in it.
So if you have one at the same level, how is it able to determine which of those nodes to point to begin with?
If you have one at the same level, how does it determine which of those nodes to point to begin with? You would have to add a new parent to both of them. Yeah.
When you added B, why did you move I? Why did you move B?
When I added B, why did I move D instead of I? Because we need to end up with a semi-ordered linked list between the leaf nodes. And in order to maintain the correct structure of their parent, anytime you split a node, you take the smaller half and move it into the left page, and the larger half and keep it in the right page. So I moved D because D is less than I. Okay. So here would be the full tree if we add, sorry, one more question first.
So how do you know, like, does that mean you'll have to look through your small list to find out what's lesser than I and then move it over? Or
So when splitting a page, yes, we have to kind of just look through the whole page in order to figure out how to split it. In reality, the way that would work is you probably just sort the page so that you know, and then you just take half of it, move it to the left, leave the other half in the right. Yeah.
As you're rearranging the pages, or the notes, doesn't that require a fair amount of page accesses and like?
Yep. As I'm rearranging these nodes, these pointers and everything, these pointers are in a page somewhere. If I have to change a pointer, I have to load that page to do it. But remember, this is going to be a very shallow tree. The number of nodes that have to change is at most the height of the tree, plus, like plus 1 or 2. But it's bounded by the height of the tree in like big O complexity. Okay, so here's the full tree containing 10 things. So a couple things to note is pages can be non-full. Both leaf nodes and internal nodes can be non-full. So I have a couple internal nodes here that are not full. My leaf nodes happen to be all full, but they don't need to be. And now I can find any key with just 3 page accesses. But that's because this is just a ternary tree. Here's a quad tree. As you increase the branching factor, the height of the tree gets much, much smaller. So we would always deal with a much bigger branching factor than just 3 or even 4. It'd be like 100. So let's kind of analyze this a bit. How does this actually work in terms of performance? Say I have B branches per node, so my branching factor is B, and I have n total nodes. That means I have log base B of n total pages visited for any lookup. So when I say we're analyzing this for performance, remember that we're concerned with I/O operations. We're not really concerned with like algorithmic complexity, which is still going to be fine for the most part. Okay, so compare that to just doing binary search on the pages. Let's say your pages, you had an array of pages that were sorted. You had enough information like at the beginning of the page to say like this page contains A through F or whatever. Then you could do binary search on those pages and you'd end up with log base 2 of n. With a BST, one possible other option, we don't really know. It kind of depends on how nodes were sorted, like how many pages do you have to access. Totally depends on the path you take through the tree. So, okay, how much better is log base B than log base 2? And we'll just ignore BSTs. We're not going to use a BST. Let's look at a typical example. Say we have 100 million total records. Like Facebook users, they have even more than 100 million. And let's just say that I can fit 100 keys per 4096 byte page. So that actually means my keys are fairly large. They'd be like 40 bytes, which is big for a key. Which would leave me with 100 million divided by 100 is 1 million total nodes. So branching factor of 100, 1 million total nodes. With a B+ tree, that's 3 pages to find any key. With binary search, that's about 20 pages. With a BST, who knows, somewhere between like 10 and 20 pages, depending on how lucky you get. So this extremely wide branching factor of 100, very wide tree makes the depth of the tree super shallow, and I can get any information I need with just 3 page accesses. And this is not algorithmic complexity. This is I/O complexity. It might be slightly more computationally expensive to do this because each of these traversal steps through the tree, would be more than a traversal step through a binary tree. Okay, so how does this actually look when making this an index in a database. So we've been, up till now, just kind of looking at abstract B plus trees. But how do we actually take that and represent database tables with it? So as I already said, every table has a primary index, which means it has a primary key, and there is a B plus tree built on that key. This is also sometimes called a clustered index. So you may have heard that every table has a clustered index. That means this is the index that actually holds the table, like the actual records in the table. So the way it works is the internal nodes hold just primary keys, and the leaf nodes hold rows in the table. So I have here, whatever the primary key is, it's these like E and C and G, these letters. Every little mini table in these leaf nodes has one of those letters, plus maybe some additional columns, like integers, dates, whatever. So the table itself, whenever I've been drawing tables in a database, I've always drawn them as one table. Every row is in one table. You can think of them that way, but in reality, the table is actually split up into mini tables spread across all the pages, the disk pages that it occupies. And then, so let's kind of look at a more concrete example with, instead of just like A's and B's and stuff, let's look at students. So UID, name, and GPA. We have the actual records themselves. I always draw that as a table. And then in addition to that, we have this little tree kind of built on top of it. In this case, UID is the primary key, so UID is the primary index. Couple of interesting things to note here. Look at the primary index and note that it does not actually even hold every key. It doesn't need to. Just having the 3, the 4, and the 5 in there is enough to get me to whatever page I need that holds the row I'm looking for. So I don't even have, look at Harry and Hermione, their keys are 1 and 2. I don't have 1 and 2 in the internal nodes of the tree, because as soon as I get to 3 and go left, I know whatever is there is going to be less than 3, so I can just search that page for 1 or 2 or whatever I'm looking for. This is one benefit of a B plus tree that makes the tree itself actually very small. You don't have to hold every key. In fact, you hold very few keys relative to the total number of keys. And then the other interesting thing to look at here is I have gaps in the table now. So every 2 rows is 1 page. And this is the clustered index. So these are ordered based on the UID. But I have gaps here now because this is basically just dependent on the order that I built the tree. Right? Anytime I have to split a node to make room, I'm going to end up with 2 half-empty nodes, 2 half-empty pages. And the way that looks, if we draw it as an actual table, is the record for Hermione might not be right next to the record for Ron on the disk. There might be plenty of space in between them. Okay. Now what about the secondary index? We can add any secondary index we want, and they work in a kind of different way, because they don't hold the actual table rows. What they hold is, so the basic idea is the same. They hold keys in the internal nodes, but then the leaf nodes don't hold miniature tables like this. The leaf nodes hold just a pointer to the real table. And when I say pointer, what we actually do is we don't hold like the location on the disk. We just store the primary key, because that is in some sense a pointer. We can use the primary key to go search through the primary index to find the row. We'll talk about why we do it that way. That might seem like extra work. Why not just have a direct pointer to the record? But let's just look at how this works first. So same table, but now I'm showing the index on GPA. So I have this auxiliary structure, which is just the tree. And then in the leaf nodes, I have the GPA key, so something like 3.5, and then paired with the primary key for whoever had the GPA of 3.5. So my leaf nodes now have a very different structure. They don't contain pointers to records, or sorry, they don't contain actual records. They contain pointers to records in the form of a key. So we can look around this. So like look at the bucket on the right has 2 things in it. So somebody had a 4.0 and their UID is 2. Somebody had a 3.9 and their UID is 3. Now what this means is here's the primary index, part of it anyway. I'm only showing the pointer to the final page holding Neville. If I'm actually doing a lookup there, I first have to search through the GPA index. So say I'm looking for someone with a GPA of 3.7. So I search through that index to get down to that leaf node. And then I have to take that primary key and kind of go through the same traversal procedure, but using the primary index in order to get to Neville. So now I have to look through 2 trees to find the row I'm looking for. So why not just change it so that the secondary index has like a direct pointer to the location on disk? So like which sector is it in, which bucket is it in? The reason has to do with primary records can move. So if I had a direct pointer to its exact location on the disk, then what happens if it actually moves on the disk? And we saw this. I was in the middle of building this tree. I'm about to add a new key. I and D are in the same page. They're in page A. So if I had a secondary index saying D is in page A, and then suddenly I add a new item, D has moved to page B, and I would have to go and find my secondary index and update every pointer for everything that has moved into a new page. So that's basically why we don't do that. We save just the primary key, and then if something moves to a new page, that's fine. It still has the same primary key. We can use the secondary index. It will have changed a little bit, but we can still get to it quickly without having to change every single secondary tree anytime something moves to a new page.
So in the cluster index, if the leaf nodes actually hold the data table, does that mean that they can't carry as many primary keys as the other nodes?
Yes. So the question was in the clustered index, which is the primary index, the leaf nodes hold actual rows, which are probably a lot bigger than just keys. So yes, they can hold fewer, probably can hold fewer entries than the leaf nodes of a secondary index.
But what about the other nodes in that actual tree? Because
The internal nodes of the tree?
internal, because they don't hold the data, they just hold
The internal nodes are still about the same. All they're holding is keys. So primary index versus secondary index, if you're talking about internal nodes only, they're probably about the same. They hold keys. Say a key is usually like 4 or 8 bytes or something. The biggest difference comes when you're talking about leaf nodes. Primary clustered index, the leaf nodes hold actual rows. Secondary index, the leaf nodes hold just the key pair that allows you to get to the actual row.
But in terms of page sizes, like the leaf nodes have the same page sizes as the internal node.
Yes, every node has the same page size. Page size is fixed, 4096 bytes. So how many things you can fit into a page depends on, is it an internal node? Is it the primary index? Is it a secondary index? Yeah. So the branching factor is not always just like 100. The branching factor changes based on how much you can pack into a page. Okay, another trade-off. Why do we sort the internal nodes but not the leaf nodes? if we have a sorted internal node, we can do binary search to find which branch we need to take. But we can't do binary search if it's unsorted in the leaf node for finding whatever we need. The reason for that is every single insert or delete is going to modify a leaf node. So every insert or delete would have to resort a leaf node. But very few inserts and deletes are actually going to require splitting or merging a bucket, which is what modifies a parent node, an internal node. So we keep them sorted because the sort is rare, and it makes traversing the tree a lot faster. And correct, like it would be impossible to traverse this tree if the internal nodes were not following the right structure. Plus, this is ignoring the fact that the thing we care about more is how many pages do we have to load. Once you've loaded a page from disk, it's not a big deal to do like a linear search through it. It is, but loading the page is the bigger deal. Okay, so back to this question of picking indexes. How do we pick the primary or clustered index? Well, we don't really. The primary clustered index is always the primary key. So we do pick it in some sense, but we pick it at the relational model level. You know, whatever we decide this relation's primary key is, that is going to be its clustered index. So what we actually end up with when we create a relation is, you just remember, you're actually also going to get a tree associated with your primary key. Okay, let's think about this, though. Let's say that UID is the primary key, and let's say I have a lot of other secondary indexes. Maybe there are more columns here, and I have a lot of secondary indexes. And then let's say I do this: update students, set UID equals 6, where UID equals 5. So basically, I'm changing somebody's UID. Obviously, that's going to have to update the primary index. And the way we do that is delete the existing one and add the new one, because that's the way to do it and maintain the correct structure of the tree. You can't just go find it and change the number, because then it's in the wrong place within the tree. But then look at this as well. Here's one of the secondary indexes. The way that it points to a row is by holding the primary key in a leaf node. So if I change Neville's UID from 5 to 6, I then have to go find 5 in every secondary index and change it to 6 so that it points to the right place. What this means is don't change primary keys. Your relational model should be designed in such a way that an ID is an ID. It's unique. It'll never change. Like, I've been at this university for a very long time. I have the same UID that I had way back then. The other thing is that I already talked about. In fact, I said this on like the first day of class. Make your primary keys small. This is why. Is because they are copied into every single secondary index as a way of finding the primary row. So the smaller they are, the less space that copy will occupy, and the fewer pages you'll need. Okay? Yeah?
Is there also an advantage to being able to fit more small primary keys on one page?
Yes, there is an advantage to being able to fit more keys per page. Yep. Okay, so what about secondary indexes? Well, we kind of already talked about how to pick these. You just have to think about what are your common queries and what index will support that kind of query. So you have to think about, am I searching by title and author? Am I searching by title or author? Things like that. And you have to remember, you're not just using one table. If you're doing a join between two tables, depending on what column you're joining on, you might want a key to help that join go faster. And so that's basically it for secondary keys, is don't ever add, secondary indexes. Don't ever add one that you don't need, because they have to be stored somewhere, they have to be updated all the time. It just makes everything else more expensive. unless you are searching using that index. Then it will be worth it. And that's about it for secondary keys. It's simpler to state what you do, but it actually might require more thought. You have to try to predict what your common queries are.
So in SQL, you can specify that a column that doesn't necessarily put an index on it.
So you can specify a column is unique that does actually implicitly put an index on it. Yeah. You can also, without even having that though, you can also just say directly put an index on this column, even if it's not unique. So these B+ trees have no uniqueness requirement. That's important. Okay. That'll do it for today, but we will see this in action with actual SQL commands. Like you'll see, it makes a vast difference in performance. We'll get to that on Wednesday.